So the definition of geometric isomers, well, first of all, it is a type of stereoisomerism which involves a different spatial arrangement, and it only occurs when there is a double covalent bond between carbons. And the reason for that is that there is restricted rotation around the double bond, which we'll try and describe a little bit later on, but it's worth considering that if you have a double carbon-carbon bond or a double bond full stop, that leads to restricted rotation. So it just means that the groups around on either side of that double bond can't rotate freely about that. It's like holding two pens in both your hands and trying to rotate it. The pens will have to slide over each other, and that won't quite work. So I've just added that in for good measure, and I really kind of want to highlight this idea of restricted. Don't say there is no rotation. There is a slight bit of rotation. It's not completely rigid around the double carbon-carbon bond. So just make sure you don't misuse or misinterpret this word as no rotation. It's restricted rotation. Okay. So in order for a molecule to exhibit geometric isomers, it must have different groups attached to either side of the carbon. Now, doesn't mean that there must be 4 different groups attached to the carbon atoms in the double covalent bond. It just means on one side of the molecule there must be at least will only be two different groups attached. So I've just mentioned that there. So this only occurs if there are different groups bonded to each carbon. Now, an example, I'm going to pop an example just down here. So there's the molecular formula of a substance. It might be worth pausing the video and see if you can draw the structure of that molecule, as many structures as you can. So it might be worth pausing the video at this point. So hopefully you've had an opportunity to draw some molecules. I'm just going to go ahead and show you what I have. And I have these 2 molecules here. So I've got this one, and you can see I've just I've drawn the groups that are attached to these carbons in different colours, just to kind of highlight what's going on and where they are. You can see that quite clearly on this carbon here, there are the hydrogens at the top and the chlorines at the bottom, whereas if we look at the second carbon, the chlorine is at the top and the hydrogen is at the bottom. Now in this particular case, that means this double bond can't rotate 180 degrees to get it to look like this molecule. It will rotate ever so slightly. There'll be a bit of rotation, but it'll be quite difficult. So it's restricted rotation, but it will never get round to looking like this. The chlorines are still attached to the same carbons, but they are just pointing in different directions, which is why we describe them as different spatial arrangements. However, the molecule that has just appeared has no geometric isomerism whatsoever. So it exhibits no geometric isomerism. So this molecule here, there's no geometric isomerism. But why? And the why is quite simple, and that these 2 are the same groups of atoms or atom, and these 2 are the same, and they're attached to the same carbon. And that means that, quite simply, it doesn't matter if this bond can rotate around and round and round. It's irrelevant, because if it was able to rotate 180 degrees, it would still end up with the same molecule. And this is a common example, or exam question I should say, where they say, why does this molecule A not exhibit any geometric isomerism? And the reason for that is that there are 2 of the same groups, in this case hydrogen atoms or chlorine atoms, attached to one of the carbons. So this may also be two CH3 groups, so that's another common example, is where these hydrogens might be two methyl groups, two CH3 groups, and they say, what is this molecule, which, it might be even a multiple choice question, is which of these molecules does not exhibit geometric isomerism, and you're looking for a carbon atom where there are two of the same group. So even if these two are different, this molecule would not have geometric isomerism because you would have the same atom attached to the carbon. Now the next question really is how do we differentiate between this molecule and this molecule, because they're quite clearly not the same, at least spatially. Structurally they are the same. We can't really distinguish between the hydrogen pointing up or down on a single carbon, but when compared we can. So how do I distinguish? Now one you may have come across before is cis and trans. Now the term cis, a prefix cis, it basically denotes that things are on the same side, so groups are on the same side of that double bond. Trans, so I like to describe it as transatlantic, so across the Atlantic Ocean. It means trans meaning going across the double bond. They are the same. So in this particular case here, we can see that the hydrogens are on opposite sides. Chlorines are on opposite sides, so we call this trans. It's a trans molecule, whereas this one on the right hand side or in the middle we'll have on the cis, because they're on the same side of this double bond, so on this kind of side of it, and the hydrogens likewise they're on the same side, so we call this cis, on the same side. So cis same, trans opposite. Okay, so and what you would normally do is you would put this prefix in front of the name of the molecule. So again, it's worth pausing the video at this point and having a go at naming the molecule and see if you can get it right. Now it's definitely it is a little bit more trickier to name the molecules when you look at skeletal. So if you're struggling, maybe draw the displayed formula to help you out with that. But you want to get to a point where you can name molecules from skeletal formula. So it's worth pausing the video now to give it a go. Now hopefully you've got the names right, so let's have a look at what it should be. Now essentially on both of these, the actual name is going to be the same. I hope you realise that. So you shouldn't have two different names for these two molecules. They're both essentially the same. You've got two carbons, so it's eth. So that's the root name. The functional group is an alkene, so it's ethene. There's no position on the alkene because it's only two carbons long, so we've got ethene, and we've got a chloro on the first carbon and the second carbon. So this becomes 1, 2, different colour, 1, 2 dichloro, because there's two chloros. Just write it underneath, 1, 2 dichloro ethene. And the same thing goes here. This is 1, 2 dichloro ethene. Now so you can see that they both have the same name. The only difference is the cis and trans, and that tells us what the difference is between the two spatially. This final molecule, if you've had a go at naming that, this is 1, 2 dichloro ethene. It really, you should really notice that that is now a different name to, sorry, I'm supposed to say 1, 1. Let's do that again. 1, 1. It's not different if I write the same thing. So it's 1, 1 dichloroethene. You can see it's completely different to the others, and therefore it's not a geometrical isomer of the first two molecules there. Now this is usually what teachers would do to introduce geometric isomerism. They'd introduce with trans and cis, and then they'd follow on from that. So the problem arises when we have more than just two groups of atoms around a carbon, so not just one, a chloro on either side and a hydrogen. Maybe I'll have a chlorine, I'll have a CH3, I'll have this hydrogen there, and I might have an OH group. However, how do I then go about naming it? Now I will come back to these molecules and apply that, but that's what we're going to have a look at next. So for example, I've got these two molecules, these geometric isomers of each other. Let's just quickly spot the difference if you like. You've got a carbon-carbon double bond on both of them. You've got hydrogen here, bromine here, but the hydrogen's at the bottom here and the bromine's at the top. And on the other side of the carbon bond, OH-CH3, OH-CH3, and they're in the same position as before. So the only thing that's changed are these two groups here. But how do I offer one up as cis and one up as trans? And that's where this cis and trans prefix, so the cis and trans prefix, falls apart. So we have to come up with a different method. Now the method that's come up is using something called EZ, and I hope I pronounce this right. So Enthagen and Zusammen. So Zusammen is on the same side, and Enthagen I believe means on the opposite side, or cross. So we use those phrases as German phrases to describe the positions of these groups of atoms. Now the way we do this is slightly different to identifying cis or trans, and that is that you've got to look at the initial molecule. So let's just have a look at this one to begin with and focus on that, and we draw a imaginary dashed line going down the middle, and we only want to focus on one side of the molecule, like so. So hopefully this makes it a little bit clearer, and we can see that we're only looking at the two groups on this carbon atom here. We do this every single time, and it works a treat every single time. Now what you then need to do is you need to give a number of 1 or 2 to each of these groups. Now you need to think, right, which one's the heaviest out of the two? So hence look at the ARs, the relative atomic mass numbers from the periodic tables, and we know that bromine is heavier than hydrogen. It doesn't really matter which way round you do this. You can give hydrogen the number 1 priority and bromine number 2 priority, but as long as you're consistent and you are consistently doing the same thing over and over again. So don't worry about whether you need to give one to the lightest or the heaviest group. It's irrelevant as long as you're consistent. And we do the same thing for the other side. So here we see we've got the OH and the carbon. Best always to just look at the atom directly joined to the carbon. So I'm only going to look at the oxygen and the carbon here. And we know that oxygen is heavier than the carbon, so we're going to give that priority there, a 1, and the CH3 a 2. So we're essentially saying oxygen mass number 16 and carbon has a mass number of 12, so I'm going to give the priority to the oxygen. Now we've got a way of deducing whether the priority groups are opposite or whether they are on the same side, and we can see going across this molecule they are on opposite sides. So this is what we call an E isomer, if you like. So by putting E in front of the actual name of the molecule, we are saying that the two priority groups are on opposite sides of that double bond. Now it might be worth again pausing the video, having a go at naming the molecules or molecule here, and then unpause and see if you were right. But the way we notify this as being, or denote this as being E, is by quite simply putting E in front of the name, as we did with trans and cis, so it becomes a prefix. Now hopefully you've had a go at naming the molecule. I'm going to show you what I have here. So you've got E, 1 bromo, 2 hydroxypropanone, and that's the name of this molecule. And because they're on opposite sides, you may also be able to class this as trans. So you compare E and trans together. So you could say it's trans 1 bromo 2 hydroxypropanone, but it is more appropriate for us to use E and Z prefixes here. Now we need to do the same thing on the second molecule here. Draw this imaginary line. Give a priority to each side of the molecule. So we're going to focus on the left hand side just as we did before. I gave priority to the highest mass, so bromine's got a higher mass than hydrogen, so 1 and 2, and then The O has a higher mass than the carbon, so that's going to be 1 again. It's the same as before, and the methyl is going to be 2. So you can see that the two priority groups are on the same side, so it becomes a Z isomer. So we just have the same thing again, but we put Z in front, but the name stays the same, so it's 1 bromo, 2 hydroxy, prop-1ene. And don't forget, it is prop-1ene because we've extended the carbon chain length with this CH3, so it's now 1, 2, 3 carbons long. So definitely worth considering that if you've struggled with naming and you're wondering why it's prop instead of eth like the previous ones were. So that is an example of geometric isomerism. It's also a reason why it gives you an understanding of why we need to come up with a different system other than Cis and Trans, and we have to use E and Z, so you need to get really familiar with that. Also, I've kind of missed out that this could also be called Cis because let's put that in brackets, that they are on the same side, same Cis, but we tend to, again, like I've mentioned before, you tend to use the EZ as a more appropriate format or way of denoting that there's geometric isomerism in the molecule. So we can have a look at this question. Again, if you want to have a read through that, so which of these molecules does not exhibit EZ or geometric isomerism? You've got but-2ene, but-1ene and pent-2ene, and finally pent-1ene. So which of these, may be more than one, may only be one, exhibits no EZ isomerism whatsoever? Now it might be worth drawing them out, giving it a go, and see if you can identify any, and try and justify why you've said these molecules or molecule has no EZ isomerism. So great time to pause the video, have a go and see what you get. So I've drawn out my molecules here. Let's start with but-2ene. Now but-2ene, in this particular one, I've drawn out the 2 bonds coming out here towards the hydrogens. You don't have to do that, and you shouldn't be doing that for skeletal anyway, but just to give you an idea, these 2 are CH3s, hence they're skeletal, and you can see that you've got 2 different groups on either side of that carbon-carbon double bond, and that would mean that if I was to swap this hydrogen and this CH3 around, I would get EZ isomerism. So literally we'll be swapping these 2 around and it would be EZ. So but-2ene definitely has EZ isomerism. In terms of, so this, let's write yes here. In terms of but-1ene, and you should hopefully see some patterns here. There's my but-1ene, the carbon-carbon double bonds at the end, but unfortunately at this point we have, and again I don't usually do this and you wouldn't be expected to do this and you shouldn't do this, let's put hydrogens on there. You can see that these 2 hydrogens are on the same carbon, they're attached to the same carbon, so that this particular carbon here has 2 of the same group, so this exhibits no geometric isomerism. Okay, now moving on to pent-2ene, again we can do a similar thing. I'll put the hydrogens again, shouldn't really be putting those in, but we'll do it for illustration. We can see there's 2 hydrogens either side. You've got a methyl group here, and you've got it's an ethyl group, sorry, here, and this is the methyl group. Methyl, ethyl, these are different groups to each other, so definitely has EZ isomerism, so this is a yes. So you can try and figure out which ones I've drawn here, whether I've drawn the E or Z in these cases. If you want to pause the video at this point, before I give the answer, it might be worth for you to try and suss out for A and C at least whether they're E or Z. Now you should realise that actually they are both Z isomers because the priority groups are on the same side always, every single time, so they are all Z isomers. If they were E, they would be swapped around. Now, last but not least, we've got pentonine, and again we've got a similar situation to B, because it's at the end. You've got two hydrogen atoms, and again, like I said, you shouldn't be drawing these, but you should know that they are there. That they're two of the same atoms attached to the same carbon on one side of the carbon-carbon double bond, so it doesn't exhibit any EZ isomerism. So this is a no. So there were two molecules here that didn't exhibit any EZ isomerism. Now, what we're going to have a look at next is, why is it that there is restricted rotation? And this is something that is a requirement for you to know and describe. So when we look at a carbon atom, when it's bonded to another carbon, we have these, it's a p block element, so its outermost orbitals are p orbitals. It has these p orbitals surrounding the carbon with electrons in them. Now, what happens is that another carbon lines up next to it, so I'm going to freehand this. And we'll draw the exact same orbitals, not the best diagram, but you can see that these two orbitals here line up with each other, and as they get closer, this starts to overlap. Let's get rid of that bit there. And then you've got the other orbitals here and here. They are further away, but as they get closer, these also overlap, but the overlap is just not as strong, and the overlap of these orbitals creates covalent bonds, and we get different types of covalent bonds. The one in teal colour, if you like, that leads to a sigma bond, which we can use that symbol to denote sigma, and these give us a pi bond. Now, a pi bond is significantly weaker than a sigma bond, but when they get closer together, these are the two bonds that form a carbon-carbon double bond. So, like I said, when you bring them together, you can start to see that the kind of blue orbitals have overlapped significantly. My kind of brownie orbitals have not overlapped, nowhere near enough. It's quite hard to draw this as a diagram, so sometimes we just draw some lines, but the overlap is significantly less, and therefore makes the bond weaker in a pi than a sigma. So there is a large overlap here, so that means the sigma bond is stronger. Okay. And the kind of p orbitals that are what we say laterally overlapping, so side to side, so there's less overlap or little overlap, and I'll just put lateral overlap here, so the sigma bond is weaker. Oops, there we go. As a result, and for the sigma bond, it's worth just mentioning that actually this is kind of head-to-head overlap of the p orbitals. And again, worth coming back here and just saying that these are p orbitals. And another way of showing this is in this diagram below. You've got your pi bond here, and you've got your, let's draw an arrow going in there, that's your sigma there. Now, there is only ever one pi bond that makes a double bond, and one sigma bond that makes a double bond. So one pi, one sigma. Don't trick yourself into believing there are two pi bonds in a double covalent bond. There is only one. Just because there's two areas of electron density, like here and here, it doesn't mean there are two pi bonds. Those two areas of electron density, actually, they're the ones that compromise or form one pi bond and not two, and that's again a common mistake or misconception students have. But what does this mean for these type of molecules? Well, one gives restricted rotation, so this pi bond, if you like, here causes restricted rotation. So pi bonds have electron density above and below the sigma bond, which causes restricted rotation. Not supposed to say restricted. Let's do that again. Rotation about the sigma bond. So you just kind of got this sigma sandwich, if you like, where the sigma's in the middle, and you've got these, your bread part of your sandwich is the pi bonds, or the pi bond I should say, and it's preventing the sigma bond in the center from rotating because you've got this electron density or electron cloud above and below, and that causes restricted rotation. But what also it does, and this is something that we'll look at in later videos, is because the pi bonds are so exposed, and that's the first thing anything will react with, and the overlap is very small, and that makes it a weaker bond. It makes it very reactive with electrophiles. So there's another thing we could add here, is that the pi bond which is quite weak. Oops, there we go. Quite weak and contains lots of electron density. Let's put E density. Will attract electrophiles. Now, electrophiles are electron-seeking species. So basically, we can describe this as E+. So slightly charged, positively charged species or positively charged ions are electrophiles. So electrophiles are, you could just add that underneath. Electron, so phile means loving, so it's electron loving or electron seeking, we tend to call it, seeking species. An electron seeking species can either be slightly charged, positively charged I should say, or completely positively charged, and in that case it'd be an ion. Now that's really quite important, and that leads you on to electrophilic addition. So we can add again to this bit here. This is why, this goes a bit off topic, so this is why unsaturated molecules undergo electrophilic addition.